In your previous modules, you might have met C structures, and you might not have used them a great deal, and it's probably the case that you didn't meet bitfields. So I'm going to spend the first session here talking about structures and bitfields for embedded programming, and in the next one we'll cover something that is closely related to it, and that's C++ classes and structures. Okay. So in essence, we're going to review what structures are, how you create them, how you modify them, and how to create new data types using the typedef command. And structures are used for lots of things, for encapsulating information, to make it easier to pass information to a function or return multiple bits of information from a function. And we'll look at some examples of that. Okay, so let's start with what not to do. And that is something like this. So what are we trying to do here? We're trying to keep track of 5 people. And for each person we want to keep track of their age, weight, height, and to calculate their body mass index using this rather crude formula. Now, it probably doesn't need me to say that this is actually very bad practice for so many reasons. For a start, it's horribly repetitive, but it makes it very difficult to, say, iterate or loop over all the people and perform common operations. Or, for example, you wanted to add another person, you'd have to write 4 lines of code, and this just doesn't scale well. This is very bad practice and very naive. So essentially what we've got here are 4 properties of a person: age, weight, height and BMI. So one way to maybe manage this is to put each of those in a separate array, like I've done here. And in this example, there are a few things I'd like to point out. For a start, we have an array that is initialized with some literal constants. So person age, just empty square brackets, equals, and then in curly brackets, all the different ages for all the different people. So 25, 23, 29, etc. So there are 5 people. Now that doesn't communicate dreadfully well, but we can work with it. What we can also say is that this is an array of type int, which on an ARM processor, or Cortex-M, is a 32-bit number. On, say, my Mac, running a 64-bit processor, that might be a 64-bit number. Right, and this is an array of 5 of them. And we do a similar thing for weight, height and BMI, only we note that these are fractional numbers, so they're type float. And the advantage of doing it this way is I can now do that iteration. So if I want to, for example, calculate all the BMIs, I can set up a loop. Each person's BMI of n, I work out the weight divided by the height squared. So that's an improvement, but it's still a bit clumsy. And we certainly can do better than that. So this is where structures come in. And I'm going to start by talking about structures in the C language. C++ is, for the most part, a superset of C. Structures in C++ can do more. So let's think about what a structure is from a memory point of view, and then we'll look at the code. So what we effectively are doing is we're creating an object or a chunk of memory, which is represented by the yellow box, and within that I have got, in this case, 4 different pieces of information. In this case it's an integer, a character and 2 integers. These will be adjacent to each other in memory, and usually this will be the low address and this will be the highest address, and you might find that in some compilers, in the case of a single byte char, it skips a byte so that these are all aligned on even boundaries, even address boundaries. It might not, and there might be compiler directives to control this. The problem is it's not a given, it's not a standard that is absolutely clear. So sometimes we pack them so they're end to end, but sometimes they're not. They're even byte aligned, and that means that you're never sure how much memory this total structure takes up. So we, in general, would declare a structure as follows: struct, and then some tag, and then a list of all the data types inside it. So let's look at an example of that. So we would write struct human, and then so this is the tag or the name of the new data type. So structures are about creating new data types from old ones. And inside this structure, we have the unsigned integer and 3 floats. So that's for the age, and that's the fractional values there. And we effectively created a new data type, struct human. Let's look at an example how we would use that in C. So this is the type, struct human, and this is the name of the variable, person. Having done that, we can now set each of these properties, person.age equals 25, and we do weight, height, and BMI. And we can print out the BMI. So the important thing to note here is where instead of writing int x, for example, where int is the data type and x is the name of the variable, we could write this, struct human, that's the type of information that person holds, and person is, if you like, the variable or the instance of that. And you could have many of them. So to stress this, that's the data type of person. Okay, so that's one way of doing it, and you could have many instances of human doing it that way. If we only want one, we can write it in a slightly more short form. So that would be struct curly brackets, the properties, and then the variable name. So we can now work with person directly. Person.age is 25, weight, height, etc. The problem with this is that this is where you want a one-off, a singleton, a single instance of it. And here we would say that this is the data type, this complete thing. All right. So you can use either method. Now, one of the most common errors in programming is forgetting to initialize variables. So let's look at ways we initialize structures, because until we've initialized them, we can't really do much. So here's the structure. The tag is human. So the data type is struct human. And we initialize it, or this is one way of doing it, with the curly bracket. So in the same line as we instantiate person, so the person is of type struct human, we say that therefore the age is 23, the weight is 80.1, the height is 1.75, and BMI set to 0 because we don't know what else to set it to. We can then calculate BMI. So you can initialize using this curly bracket and comma separated list, and this matches the first one, this matches the second, and we've got to be careful to get them in the right order and of the right type. And the problem with this actually is that this is often tucked away in a header file, maybe buried deep, long way away, and you've got to remember what all the properties are and in what order, so you have to go find that information so that these are in the right order. And if you're looking at this code, it's not obvious that that, for example, is the height. You could probably work it out, but it's not explicit. So these initial values, these are what you call literal values, actual numbers or actual characters or actual strings that you hard code into your program. They're okay, but you need additional comments to explain what they mean. Better is the second approach, where you can actually label these values. So that's the data type again, and the initial values now have labels. So .age is 23, .weight is 80.1. Now we don't really need a comment to explain these anymore. It's sort of self-documenting, and that would be preferred. Okay, so that's initialized structures. Now another thing to note, all the properties of human at the moment are your baked in data types, so unsigned int and float. These are what we call value types. So wherever you refer to an integer, so if you had int x equals 10, wherever you reference x, what we're talking about is the value stored in the variable x, 10. All right, and x equals x plus 1, we are incrementing the value of x. Of course, under the hood, addresses are used. So the address of a variable would be used. And when you're dealing with address in C, we call it a pointer. And in computer science, it would often be referred to as a reference. Right. So when we hear the word reference or reference type, we're usually talking about pointers in the context of C and C++. So something you can say about value types is that they obey what's called copying behavior. And structures that contain only value types are also pure value types. So let me explain what we mean by that. It comes down to what we mean by the equals or the assignment operator. So this is the type, struct human, person. And we've also created another one called person2. The first one's initialized with some literals. The second one is simply equated to the first. And what will happen is you'll get an element by element copy from person into person2. Now it's very important to maintain the fact that they are value types, they are independent of each other. So this person2 is a copy of person, but it is independent. So if I was now to modify person, it wouldn't affect person2. Yeah, that is because they're value types, so we get this copying behavior, which of course has a cost. There's a cost to copying all those values across. Let's look at a little demo of this. Now, this is a recorded demo in the slide. I'm not going to play the audio, so I'm going to pause this and just talk you through it quickly. If you look in the slide, there's a longer discussion. So what I've done here is I've created a struct complex. All right, this is a new data type called struct complex, and it has two parameters, real and imaginary. Okay, and I've commented out some function declarations here. So I want to start doing some useful things with complex numbers. So let's start by creating and initializing a complex number. So the type is struct complex, the variable name is cval1, and we initialize it with 0, 0. So 0 for the real, 0 for the imaginary. I didn't use labels in this case. Okay, and if I create another one, cval2, and make it equal to cval1, then that will make a copy of cval1, but it's an independent copy. All right, we can build that, and we see that that's fine. So now let's do something interesting. Let's display these two things. So I'm going to write a function that takes a complex number as a parameter and prints it out on the screen, called complex display. So we write the code, get rid of the semicolon, and printf, two floating points, put a j on the end, and then we need to now put in the real and the imaginary. So the printf has got two placeholders for two floats, that's the c.real and c.imag. Now something to point out is when we call this function, you'll pass a copy of a complex number, right? So a copy of the whole structure will get added to the function stack. Every function has a stack space for all its local variables and its parameters if it uses the stack for parameters. And C will exist independently of anything else in the code. It's temporary. It only exists for the duration of the function. It's like a local variable. Okay, so let's call that function with cval1 and cval2, and when we run it, they're both printed out. So notice cval1 is passed as a parameter into complex display, and the data type and the argument name is there. So these are copied, right? cval1 and 2 are local to main. They're not visible from this function. All this function can see are global variables, which we haven't got any of, and this parameter c. So now let's change cval1 to 1, 0, cval2 to 0, 1. Run that and we see, indeed, these values are displayed. Okay, so let's now create a new function which calculates the complex conjugate of a complex number. So again, we're passing in a complex number. We're going to create a temporary result of the same type and return it. So look at the return type. It's complex as well. So look at what we're achieving here. We're managing to pass two floating point numbers as a single parameter in the argument, and we're managing to return 2 in the return type. Now in C, you can only return one thing, but the beauty is if you use a structure, you can encapsulate many things inside it. So complex. So what we do is we create a temporary one called result and equate it to C. So when we call this, a copy will be passed as a parameter. That will then get copied again into result. We manipulate the result by negating its imaginary part, and we return a copy of that result back to wherever we call it from. And so when we do this, okay, let's just get to the point where we want to see that. There we go. So cval2 equals complex conjugate cval1. So 1 is passed into here, a temporary one is created, and that one's copied into it. You negate the imaginary part, return this, and then that is copied into cval2. So quite a lot of copies in there. All right. And what you'll find when you run that, you'll see that indeed the second one is just the conjugate of the first. It's not terrible. It's very readable. If you look at this code, I think we can all follow this even with no comments, because I've chosen meaningful names for things. All right. Moving on then, let's look at adding. So this is slightly more complicated again because it takes two parameters, two complex numbers, returning another complex. So again, we need a result, a local variable to hold the result. We copy C1 and we add on the C2 real part. And then we add on the C2 imaginary part, and we return the result. So again, able to return complex data structures by using a single structure. Finally, let's invoke it and display it. And there we see the sum of the two is 2, 0. A complex number plus its conjugate is real, of course. So that's using structures to encapsulate two floats and to make our code more manageable and easy. I'm going to talk about typedef in a minute, but let's have a quick sneak peek of it in the video because I've kind of got ahead of myself here. So another way to create a data type is to use typedef, and it works typedef old data type new name. Okay, so we can do this. So what this means is complex is an alias for struct curly brackets double real double amount curly brackets. So now we can get rid of this struct word everywhere it appears and just use complex because that's an alias for struct. Okay, and all the rest of it. So very quickly whiz through this, and what we'll find now is our code is getting tidier now. Now we can just go complex as the data type. Right, so that is an alias for all that. I'll explain that on the next slide. So typedef. In simple terms, these are used a lot actually in embedded software. Old type, new type. Okay, so this name is an alias for this. So for example, we could have created our own int32 as an alias for int, which on the ARM Cortex M4, that's a 32-bit processor, and its integer is in fact 32 bits, whereas on another one it might be 64 or 16. So typically in the header file for a particular microcontroller or microprocessor, you'll have a set of typedefs with new definitions of baked-in integers and floats and so forth, with the number of bits, like uint32, for example. A bit more of this later in the course. The main thing you need to know right now is the syntax. Typedef, some existing typedef type, and a new name. All right. So, for example, typedef unsigned char is byte. All right. So the old type is unsigned char. The new name for it is byte, and so we can use it to create variables of type byte or arrays. And if we run this code, we can just print them out. Now, where typedef gets especially useful is with structures. So let's look at that. That's what I did in that demo. Remember the syntax. So we would use typedef the following way. Typedef struct, and then all the properties, and then the new name, port data. Right? And now we can just use port data as the type. So port data, my data, port data, your data, or an array of them. Yeah? And we use the dot notation to access the individual properties of any instance of port data. Okay, so of course these are all independent of each other. And this is nice because it's sort of cleaner code. Now there are varying sort of rules, or shall we say conventions, for naming. Some companies like to have a capital letter for a type, so it would be a capital P for port data. And actually that's what I usually use. It does depend. Right, so be aware of that. Naming conventions. The compiler won't enforce them. These are single instances of type port data, so type variable name, or of course we can have an array of them and iterate through them and modify, etc. Okay, so remember we read and write the dot notation when they are value types. So this is a variable, a value type. If we equate this to another, it will copy it, and when we know we're using them because we use this dot notation. Okay, so this is nice because this horrible thing, which does not scale well, you end up with a total mess in your code. We could now do this. We can type back to our BMI application. We can encapsulate all the sort of relevant properties for a person, and we've got person type. So person type, person 1, person type, person 2. Okay, it's getting there, but much better is of course to have an array of them. So all people are inside an array. We've got an array of person type. And we can initialize that, for example, with a for loop. And as I think is apparent, this is a lot better than the previous approach. Right, so something else that comes up in embedded software development, you probably wouldn't see it on desktop programming very much, is bitfields. And bitfields need structures. They're an interesting language feature designed to help you manipulate, set, reset, or read bits, individual bits. Okay, so this is an example, and there's a reason I've highlighted that, and I'll talk about that in a minute. So we've got a typedef struct audio processor. I just made this up, and that structure has a number of properties: sampling rate, scaling, input sample, output sample, a boolean whether on or off for a filter, and a set of most significant bits. The difference here is that although this is unsigned integer, we've got a colon and then the number of bits that it actually needs. And that's interesting when we get to say scaling, which is an 8-bit number. Now notice I haven't used an unsigned char, and the recommendation is you don't. All right. The general rule is stick to integers, unsigned integers. All right. And then specify the number of bits afterwards. You could have an unsigned long, that would be okay. Now, if it's a single bit, like this one, it can only take a value 0 or 1. Right? It's still an unsigned int, but it's a 1. That should never be a signed int. So for a single bit, it's nonsense to have a signed. You've only got 0 and 1. So you should always make it unsigned for a single bit. The others could be integers. Anyway, the key thing is we say how many bits each one occupies. Now, how that's laid out in memory does depend on the compiler. For the compiler I was using when I wrote this slide, there's this additional attribute called packed. It's a compiler specific directive which forces these to be packed in end to end. So we've got 16 bits, and the following 8 bits is this one, and the following 16 bits is that one, the following 16 is that, the following 1 bit is that, and so forth. However, there's no absolute documented guarantee that that's what will happen. So you would need to check your compiler documentation, use the right directives, and put a comment in to explain how the memory is laid out. You do need to know that information before you use these things. Okay, never assume anything. All right. So basic guidelines: use int, unsigned int, or in the case of C++ Boolean, do not use char or enumerated types, which we'll talk about later. Single bit should always be unsigned. This is nonsense to talk about signed. Check the compiler documentation, look at the rules, and use any directives that are provided. Let's look at another example. This time I've brought in something new. It's a union. And this is a subject for some reason seems to confuse students. All a union does is put two data types or variables, if you like, at the same address. Right. An example is probably going to help. Let's start with the union itself. So union, curly brackets, and then the data type name, port data. And what we're saying is that port data has two properties. Port bits, which is a structure, or port 16, which is a 16-bit integer. But here's the rub. Here's the thing. Both of those have the same start address. Now, in structures, it's low address to high address in the order they're written. With a union, they have the same start address. In other words, this structure and this unsigned integer are not separate. They are the same piece of memory. The only difference is the data type, and that basically dictates how we modify it in our code. But at the end of the day, you're modifying the same piece of memory. Let's look at an example. So this is our data type, port data, and I've created an instance of that called myPort. Now, it's got two properties, port bits or port 16. Port 16 is an unsigned short, which on this compiler was a 16-bit. So my port 16 equals the literal scalar 0. So that is 16 zeros in binary. Right? So this union, this variable, my port, is 16 bits wide. And we can treat it, if we do port 16, as an unsigned short and set all the bits. Or we can set it to any 16-bit value we like, all the ones, all the zeros, any pattern you want. And that's great because you can hit them all at the same time and they all change at the same time. So a common example is to reset all bits, which is what I've done there. Now I want to access individual bits or bit groups. And that's where I change my view of the world by referring to my port, not with port 16, but port bits, which is the other property. Now, port bits is a structure here. And within that structure, we've got these properties and their bit fields. So the least significant 4 bits is called X. The next most significant bit is EN1, etc. So look what I can do. I can go my variable port bits. So that's saying, okay, it's that property, but that property's got its own properties. These things, .en1 there. So this is actually setting bit 4. Remember, we start 0 to 4, right? Of this piece of memory without affecting any of the others. We are, of course, assuming that these are packed end to end, no gaps. Again, refer to your compiler documentation. All right. So the nice thing about this is it's intrinsically or inherently sort of readable. Right? You can look at this, and without knowing the bit position of that enable EN1, you can just write code that clearly expresses the fact that we're setting the EN1 bit high. And this, as you can imagine, is great if you can overlay this with some of the standard registers in your microcontroller, for example, so that you can have everything assigned by name as opposed to bit position with ors and ands and all this horrible stuff. Okay. Using the same example, sorry, I'm getting ahead of myself. Yes, using the same example, let's look at it from a memory point of view. So bit numbers 0 to 15. The first 4 is X, then it's EN1, then EN2, then there's a blank. Now notice this blank here. There's no label. So we're just burning 9 bits. And then the most significant bit is CE, which probably stands for chip enable. In parallel to that, we can look at it as a port 16 instead. So we've got port bits of port 16, and we just see that as a 16-bit wide number. So whether you modify the individual bits or that one, it's all part of the same 16 bits of data. All right. And as I said, these are commonly used in embedded stuff where you're dealing directly with hardware. All right, but do check the compiler docs and be careful about the layout in memory. Make sure you're clear. All right, so that's bitfields. In case you've not encountered that before, it's a useful language feature as long as you're careful. Now let's go back to structures and how we might use them to pass data to and return back data from functions. So let's look at one without using structures first. Add this. It's adding two integers and returning an integer result. So we pass in A and B. There'll be copies, probably in registers, but maybe on the stack. Compiler specific, not to worry about that. We create a local variable on the function stack called y. We set it to a plus b, and we return this result. And we invoke it like this. So p equals add this, x and y. Now, we could inside here modify a and b, but they are independent copies. It wouldn't affect x and y. Okay, because these are passed by value. So again, copies are made when we pass this, at least logically speaking. All right, so arguments are copied onto the function stack. In practice, if you turn on optimization, all sorts of clever tricks may happen to make this work faster, to avoid some of the copying. But from your point of view, logically, it's identical. All right, local variables a, b, and y are on the function stack, and it only exists for the scope of the function. Once you hit the return and leave this curly bracket region, they are inaccessible. The word is forgotten. They're never deleted, they're forgotten. And note we are returning a single data type because that's how C functions work. Let's do something similar now, slightly different because well, the follow-on slides will do this in different ways. So let's look at a new type called point. It's a structure. It's got two properties, x and y, and we want to flip the x and y coordinates. So do flip takes a point as a parameter, a copy, creates a temporary one, sets the x to a's y and the y to x, and returns it as a return type. Nice thing about this, if we'd done this by passing x and y, we'd have to pass two parameters and our code would be longer. So there's only one parameter to pass, or argument. Point kind of says what it is. It's a point, it's a Cartesian point, xy coordinate. So it's got sort of self-documenting properties, and we can return complex data types in one thing. That's one of the nice things about structures. The thing you've got to watch is that when you pass a structure as a parameter, you're passing a copy. All right, it's a value type, so it will be copied. Now, what happens when you call a function? Well, here we're in a function. Don't know what it is. Doesn't look like it's main because it's got a return address somewhere on its stack. All right, so this is the beginning of the function stack, and this is the location of the next free space on the system stack. So we've got some stuff on here, a couple local variables and a return address. You might have some parameters on there as well. And then you call a function passing a structure, or maybe passing multiple arguments. Sometimes those function arguments get copied onto the stack. If you've got very large sets of arguments or parameters, we call them, or many of them, then there won't be enough registers to hold those, so they will typically end up on the stack, as will local variables, as may a return address. And while the function is running, they persist. All right. Then you get a result that has to be put somewhere, again compiler specific, and then finally we return from the function, and all that happens is that the stack pointer is put back and the frame pointer, if it has one, is put back. Now actually that data is still here in RAM. All right, so if you were maybe holding any passwords or encryption keys in a variable, you might want to zero them out before you return, just a sort of side thought. Okay, because when we return, it's a fast, efficient operation, so all you got to do, all the compiler has to do, is insert code to put the stack and frame pointer back. All right, and therefore these are not accessible, although they may be kicking around in memory. They're going to get overwritten on the next function call. All right, Now, there's a lot of copying going on. So as you can imagine, taking that at face value, ignoring optimizers for a minute, that would seem to A, stress the stack, makes it rather large, and also there's a cost to all this copying, so there's a performance hit. So one of the things that you see done is that you don't pass a copy of a structure, you pass the address of an existing one. Right? So this is do flip, which is reversing X and Y, but there's something subtly different about this, and that is these arrows. So notice we take the address. This is a point star, means this is a 32-bit number, and it is the address of a piece of data that has the type point. So knowing that, we know how the compiler knows how to work with it. So we create a temporary point P, we set X to AY, Y to AX, and then return P. So there's still a copy going on because we've got to get the return result back. All right, but that's passing an argument by reference. In other words, you're passing the address of it. So that's a pointer or the address of a structure. And note when we're dealing with pointers, which we are with A, we use the arrow notation instead of the dot. Okay, and that's a good reminder that A is actually the address of the original. Right, but in this case, we're returning a copy of the temporary one P. So there's still a bit of copying going on. So we could modify this further, and we could do in-place modification. Now look at the difference now. No return type. So A, the address of a point is passed in. We create a temporary variable to hold AX. We set AX to AY. We set AY to what was previously AX, and then we quit. And so what we've done is whatever's been passed in here, we've got the address of it, we've modified the original. Right, so we've overridden the arguments. So there's no copying of data, and there's no copying to get the return back. We actually modify whatever is passed to it. So nothing's actually returned, which you would think is faster, and in some cases it will be. And this is how you'd invoke it. So we've got a point, my point, we set X and Y, and then we pass the address of it. And when this function returns, you'll find that my point itself has changed. The X and Y values will be switched around. Now the trouble with this is you can not realize that this function does an in-place modification. There's nothing in the name to say that. You could probably guess it because you're passing the address for a reason. The trouble is that reason might be for efficiency, right? But what if the reason is because it's in-place modification? Could be quite a, if that could be surprising to you. You didn't think that my point would get changed. Well, it's been changed. All right. So on the next slide, there is actually a video.
In this demo, I want
going through that. I suggest you watch that yourself and listen to the audio track. Let's have a quick scrub through it. So we've got this type point, X and Y coordinate. We've got do flip, which actually takes a copy in and returns a new one. Okay, so P2 does a flip of P1. So it'll be 3-2 instead of 2-3. And we can see that coming out on the screen, no doubt. If you watch through the video, it uses the debugger to show you what's going on. So that's that way. As you can see, 2-3 gets flipped to 3-2. And then we're going to modify it now to use in place. And so forth. So watch this video. As I said, I'm not going to go through it all now because it makes this very long. The video is also available separately on Panopto. Let's get on to some important things. Now, when you pass a pointer to a function, you might want to communicate that actually I'm only doing this for efficiency. So in other words, I can guarantee that the thing you're passing won't get modified. Now there's two things you could modify actually, and we'll come to that. So we use this const keyword. Now this confuses most people. Used out on its own with a single variable like this, const double, that's the new data type, fval equals some initial value. Once initialized, the value of that variable cannot be changed or mutated, as it's sometimes called. Okay, so with const before a data type, what you're saying is that we have a read-only version of this. So once it's initialized, that's it. You can't change it. Okay, so f value will be 3.1415926 for the rest of the code, right? If you try in your code to modify it, the compiler won't let you. You won't even get to build the program because you've already said this is read-only, yeah, and therefore you cannot subsequently have a statement that goes f value equals 0, for example. It just won't compile, and that's good because not compiling means that you've made a mistake and it's found it for you before the embarrassment that you've actually allowed the code to run, right? It's not a runtime error, which is the worst type of error. Now, if you have a pointer to a float, as you've got here, so f value's type isn't double, it's double star, which is the address of a double, right? Which we could set to anywhere in memory. By putting a const on the front again means you cannot modify the value stored at that address. So it's semantically very similar to the one above. Where you get confused is the third form, is where you write the const after the data type, and that only really applies to pointers. And what this means is that the pointer cannot be changed. So once f value has its address set wherever that is in memory, presumably there's a double at that location in memory, right? If this is to work, you cannot then change the pointer. It's fixed to that address. Or you could do both, right? So we have a pointer that's fixed to a place in memory and the value cannot be changed. The compiler won't allow it. So if you're looking at a header file and you see a function with const double star const, right? You know, we're safe. There's no way that what I pass to it can be mutated, can be changed. So it's only doing this for efficiency. This is a speed thing. All right, so that's const, and you see that used a lot. So to summarize, structures are a great way to encapsulate information, group it together, and it makes code more readable, it keeps it shorter, but be careful about memory layout, especially with bitfields. All right, go look in the documentation and find out how structures are organized. Is there a way to force them to be packed? That is likely to introduce a chance of slightly lower performance because we're off, particularly if we've got odd addresses and turning up. It is compiler specific. Unions, well, one thing you can say about unions is that everything listed in a union has the same start address. Again, be careful with when you're using bitfields inside structures that everything is laid out the way you think. Just because you've unioned two things doesn't mean those things are arranged the way you imagine. Passing and returning whole structures to and from functions, you can do it. Now, this is a very difficult one to pin down because you don't assume it's faster. I think that's really what I'm trying to say. You'd have to benchmark it and time it. Right? You might find that with the compiler optimization turned on, which is not the default, usually it's all turned off to help you debug your code, but if you turn it on and build the most efficient version, you might find that passing by reference has no benefit. Okay, you might, but you might not. Okay, so don't assume because you're doing logical copies an actual copy occurs. There may be ways it can avoid it, but it's not in your control. So often people do pass by reference for efficiency reasons. Do consider using const, right, to communicate that I'm doing this for speed reasons. I'm not about to modify things in place. If you don't see a const, be suspicious. All right. Okay, very quickly, I'm going to talk about these. Again, they turn up in all sorts of code, but embedded code is not an exception. And they're basically fancy integers. Right, and what we mean by that, here's the simple one. enum boolean. That's the new data type. And the possible values you can assign to something of the type boolean is no or yes. Those literal letters. Okay. So by default, they're integers, and they're always integers in C. They start at 0 and they count up for each one you put in this list, 0 and 1. Okay. Here's another example. Months. And I've overridden the starting value. You can override any value as long as they've all got unique values. I think I need to double check that. So months, anything of type months, should be month really, shouldn't it? Can be assigned to Jan, Feb, March, April, etc. But you can also consider it to be an integer. So Jan will be a 1, Feb will be 2, March will be a 3, April will be 4, and December will be 12. And that's much nicer than hash define. For start, these do this automatic increment. So let's look at some examples of this. So type def enum. So this is the data type, and this is the variable that we're the new name. So this is the old one, enum, and it could be 1, 2, 3, or 4, or 5. And the new type is called numbers. We've overridden the starting value to be 1. All right. So this code we set n is a type numbers. And notice now when we assign n to values, we can use one of these names, and that means your code can sometimes be pretty, right? The one I use it for is state machines. If I give a name to each state, then I create an enumerated type. So, it could be initialization state, I don't know, chip select, then it might be, byte send, or whatever it is. So when you draw a state diagram and you have names for states and you're keeping track of them in a variable, good to use enumerated types, and therefore you always refer to them by their name, not by the numerical value. So it's pretty. All right. Okay, so that's it for C structures. Structures in C++ can do more, and that's the topic of the next presentation.